Right, I'm going to solve the Year 12 assessment paper now. I'm doing it on the video just so that everybody can spend as much time as they need over it, because you clearly found it quite challenging. So here goes. Question 1, this is a GCSE level question. Momentum, mass and velocity, you need to decide whether they're scalar and or vector quantities. Velocity you should already know is a vector, which rules us down to that one or that one. Mass is obviously a scalar, which is that one or that one, so we're still on those two. So you need to decide whether momentum is a scalar or a vector. Momentum contains velocity in its calculation, so it must also be a vector. It inherits its direction from velocity, so that's that one. 2. The system shown, a light rigid beam is pivoted at X and is held in position with a string here, which is fixed at point Y up here. The beam carries a load of 200 newtons, doesn't really matter what the load is, but the load is moved towards X, which of the following statements is correct. So this one, even if you can't actually work out what the answer is, you should be able to do it by process of elimination. The tension in the string increases. So first of all, if you move that from there, say, to here, then and we take moments around here, you have reduced the moment of this 200 Newton force. If you reduce the moment of that means you need to reduce the moment of this force as well, this tension, which is going to be inside that string. If you reduce the tension, if you reduce that moment, therefore you need to reduce that tension for it to remain balanced. So that's incorrect. The compression force in the beam increases. Okay, this one might be a little bit tricky, but if you think the compression force in the beam is what's squeezing it into the wall, so it's the horizontal component of the tension is pulling the beam into that wall. So if the tension reduces, then also the compression force reduces. So that's not true. The moment of the load about X increases. That's obviously wrong. The moment of the load about X decreases. So those three are false, so it must be D. So D is the correct answer. Right, let's see why. The magnitude of the vertical component of the reaction at X increases. So X is going to have a component this way, stopping the beam from falling like that. If you can imagine this was held onto there, then the beam would just slide off. If that were made of ice there, it would just slide down like that. So there's got to be some sort of frictional force acting upwards, and there's got to be a horizontal component of that acting outwards as well. Right, so if we think about moments about this point here, call that point A, then the moments about this point, this force has no moment about that point because it goes straight through it. The anti-clockwise force of this 200 newtons, the anti-clockwise moment generated by the 200 newton force here, must be balanced by the force here, which is the vertical component of the reaction at X. So that point, that force there, this moment, must counteract that one there. So if we move that way, that increases the moment of the 200 Newton force about the end of the beam here, so that force must also increase. So that is true. Which of the following is a scalar quantity? Again, GCSE level question. All these have direction, so therefore it's that one there. Right, question 4. The diagram shows a uniform meter rule of weight 1.5 newtons pivoted 15 centimeters from one end. So first of all, we need to mark on its weight because that's not drawn on the diagram. So that needs to be about halfway along, which is about there. So that there is 1.5 newton, and this distance here, well, it's got to be 50 centimeters to the very end, so that's going to be 50 minus 45 is 35 centimeters there. Is that distance there. A scale pan of 0.5 newtons is placed at the end of the ruler with an unknown weight on there. The ruler is then moved to steady horizontal position when a weight of 2.5 newtons is placed up here. Distance from the pivot. What is the weight of the object? Right, so I'm just going to combine the pan and the object together to start with. And I'm just going to call that F. So we have F times by 15, that's that one distance there, must equal 1.5 times, I don't know why I'm using pencil, 1.5 times by 35, which is that force there, plus 2.5 times by its distance to the pivot there, 60. Okay, so you need to work this out. 1.5 times by 35 plus 2.5 times by 60 is that much, divided by 15 gives you 13.5. So F is equal to 13.5 newtons. Now that means the pan is 0.5 of that, so the mass must equal 13 newtons. So it's got to be C, because those two add up to that. The pan is 0.5 newtons, the mass there needs to add up. So we just invoke the principle of moments there. That's the anti-clockwise moment plus that's the clockwise moment from that. That's the clockwise moment from that. So that's 2.5 newtons acting down like that. Right, onwards and downwards. 5. A ball bearing of mass 2m is projected vertically upwards with the speed of u. A ball bearing of mass m is projected at 30 degrees to the horizontal with a speed of 2u at the same time. Air resistance is negligible. Which of the following statements is correct? Well, firstly, you should know that the mass is irrelevant because there's no air resistance, so the mass is completely irrelevant. So firstly, we need to work out the vertical component of this here. So of the second one, I want the vertical component. So u vertical will equal 2u, and then you can either do cos of 60 or sine of 30. I'll put sine of 30 in. And if you do that, sine of 30, lo and behold, is a half. So uv for the one that's going like this is actually just equal to u. So once you know that, they're both being fired with the vertical component equal to u, and one of them's got a horizontal component as well. So the horizontal component of y's velocity is u. No, that's the vertical component of y's velocity is u. Horizontal component is 2 times by cos of 30 is root 3u, so it's 1.7u. The maximum height reached by y is half that. Nope, they're going to reach the exact same maximum height because they're going to go up and down exactly the same. They hit the ground at the same time. Yes, they do, because they both have the same vertical velocity. X hits the ground first now. So it's C. They've both got the same vertical velocity, so therefore they both hit the ground together. Okay, 6. This one is based on your understanding of terminal velocity. Well, it's not really terminal velocity, but we have 4g as the force acting downwards. We have 30 newtons acting upwards. So 4 times by 9.81 gives us 39.24 acting downwards. Take away the 30 acting upwards gives us a resultant force of 9.24 newtons. This is possibly a little bit mean of me asking this one, but it is just GCSE work. So you can use F is equal to MA, so A is equal to F divided by M, so that's 9.24 divided by 4 gives you 2.31 meters per second squared. So the answer is C. Question 7. A car wheel nut can be loosened by applying a force of 200 newtons on the end of a bar that long. A mechanic is capable of applying this force, 500 newtons, simultaneously in opposite directions to a wrench Y. What's the minimum length needed for which he needs to loosen the nut? Okay, so basically we can do it with a shorter bar than this. This is quite a long bar here. So first of all, you need the moment of a couple, which is just something you need to learn. Moment of a couple. That's probably on the formula sheet as well. So we need to work out the moment of a couple. It's not on the formula sheet, you need to learn it, but you're still using this equation here, so you can work it out from the end. It's just the force times by the length. So it's the force on either end times by the length, which is 500 L's, whatever L happens to be. Okay. So we need to find the moment of this as well. The moment of this is equal to 200 times by 0.8, which is equal to 160. So we need to equate the two to find out what the loosening force is. So we've got 160 is equal to 500 L's. So we've got 160 divided by 500 gives you 0.32 meters. So that's that one there. Question 8. Diagram shows the path of a projectile launched from ground level with a speed of 25 meters per second and an angle of 42 degrees. What's the horizontal distance from the starting point from where it hits the ground? So we're interested in the range there. So we're interested in that distance there. So here goes, S-U-V-A-T, and we've got the vertical, and of course the horizontal has no acceleration, so the acceleration is 0 time. The S is going to be the range. In the vertical direction it goes up and then it goes down again, so it's 0. U is 25 times by sine of 42. V is going to be minus that, because when it goes up and go down, like that. In the horizontal direction, U is 25 cos of 42, and V is of course the same, because there's no horizontal acceleration. V will be minus 25 sine 42. We know that because it starts and ends at the same point. A is minus 9.81, and finally T is what we're going to need to find to cross the bridge. So we need to use this side to get what T is, and then we'll use this side to get what R is. So we need to first of all do, we want the one with T in, don't we? So S equals UT plus a half a T squared is probably the easiest, because S is 0 is equal to T brackets U plus a half a T. Just taken that T out there. So either T is equal to 0, which is when it's here, or T is equal when this fraction is 0. So we need, or U plus a half a T is equal to 0. So that's 25 sine 42 plus a half times by minus 9.81 times by T is equal to 0. So let's work that out. So we've got a half times by 9.81 is that bit there. Move that over there and the minus becomes a plus. We need to divide it by 25. We need to divide it by sine of 42. Well, I've put everything on the wrong side, haven't I? So 1 divided by that. So T is equal to 3.41 seconds. So T is equal to 0 or T is equal to 3.41 seconds. We want the T is equal to 3.41 seconds. So for this one, because there's no acceleration, we can just use speed equals distance divided by time. So displacement is equal to velocity times by time, which is equal to 25 cos of 42 times by the time, which is 3.41 seconds. So let's times that by 25, times it by cos of 42, which hopefully gives us one of these answers. There we go, it's D. Right, so what did I do there? Wrote out suvat for both, used the vertical suvat here to calculate what the time is, and the time was either 0, which is when it's here, or 3.41 seconds when it's here. Then used that in the horizontal version. Now horizontal version isn't technically suvat because there's no acceleration, so you can just use your standard displacement equals velocity times by time. So that's that there. Okay. Two identical balls, X and Y, are the same height and horizontal distance of 25 centimeters apart. X is projected horizontally with a speed of 0.1. That's X, that's Y. That's 25 centimeters. I would encourage you always to draw plenty of stuff. The X is projected horizontally 0.1 meter per second towards Y at the same time that Y is released from rest. Both X and Y move freely in the absence of air resistance. What's the difference in distance between the balls 1 second later? Oh, that's trivial. They'll fall down at the exact same rate. So we're just interested in, this one's going to do that, that one's going to do that. So at any time, they'll be the exact same height, any given time. So 1 second later, let's say it's here, then that has moved 0.1 meters that way, so that's 0.1 meters. So that must be 0.15 meters, so that those two add up to 25 centimeters. So 0.15 meters there. That's that one. Okay. Long answer questions now. Here we have a pivoted system. We've got this counterweight here, and it's in a bucket with some water in, and then, sorry, the bucket and some water here, and we've got a counterweight here and the pivot here, and this is used to lift up the water. So the counterweight has a uniform material and has a weight of 50 newtons. And that's gonna, if it's a uniform material, that means its weight acts through its center of mass, which must be in the middle because it's uniform, so that's 50 newtons there. Okay, so let's think about what distance that is away from there now. That distance there, I will use my pencil now, that distance there is going to be 3.2 meters halfway along here, so we have to come back by 0.3 meters, that's 2.9 meters to get from there to there. Okay. So calculate the moment the counterweight around the pivot when the beam is horizontal. Now that's quite easy. Moment equals force times by, force times by perpendicular distance. So that's going to equal 50 times by 2.9. 50 times by 2.9 is 145 newtons. Okay, we'll leave it at 145 rather than rounding. It doesn't say put it to a particular number of SF. 145. If you put 150 here to 2 SF, as long as I'd seen that, then I could give you the mark. The bucket has a weight of 120 newtons and a capacity of 0.16 meters cubed. When the bucket is half full, what's the force required this end of the beam to lift all of this? Okay, lots of marks for this, so we've got quite a bit to do. So first of all, let's work out what the weight of the water is. So the mass of the water, that will be the first thing we will do. The mass is equal to the volume times by the density. So that's equal to 0.16 divided by 2, because it's half full, remember, so that's the capacity divided by 2 because it's half full, times by 1000, which is equal to 80 kilograms. So the weight of water, W equals mg, so that's equal to 80 times by 9.81. So 80 times by 9.81 gives you 784.8 newtons of water. Okay, and then we need the bucket as well, which is another 120. So water plus bucket is equal to 904.8 newtons. Right, now we can use the law of moments, the principle of moments. So we have total clockwise moments equals total anti-clockwise moments. So clockwise moments, we have 50 newtons times by 2.9 meters, that one and that one, that force there. This guy's presumably got to push down here, plus the force that we don't know times by this distance, because he's pushing right at the end there, so that's 3.2 meters. Oops. Is equal to this force, 904.8 times by this distance here, 1.4. Okay. So we then have F is equal to 904.8 times by 1.4. Need to take this away. Take away, that was 145, wasn't it? 145, and divide it by that number there, 3.2. So let's do that. Times by 1.4, take away 145, divided by 3.2, gives us 350.5375 newtons. So that's 350 newtons to SF. Okay. There's quite a bit to do there. You have to first of all work out the weight of the mass of the water, then the weight of the water, then the weight of the water in the bucket, and then you had to use moments. So if we do not consider the beam to have a negligible mass or weight, then how will that affect it? Well, if you think about the weight of the beam is going to be on this side of the pivot, isn't it? Because the centre of mass of the pivot, the centre of mass of the beam will be on the right hand side of the pivot. So the centre of mass of the pivot, of the beam, will be on the right hand side of the pivot. This will create a clockwise moment. So the force needed to lift it will be less. There we go. So we'll have a weight here. We'll have another force acting that way to create another clockwise moment, a bit like the counterbalance, meaning that the force he needs to push down there to lift that up will be slightly less. It will be reduced by the weight of the beam. Right, question 11 is the long answer projectile question. There's quite a lot going on here. So we have something which is above the ground being launched at an angle. The vertical component of the velocity is 5 meters per second, but it's being launched at an angle of 25 degrees. Projectile is launched some distance above the ground, an angle of 25 degrees with the vertical component 5 meters per second. This shows the path. The flight time is equal to 1.3 seconds. So we're going to need to use suvat at some point in this question, I'm sure. So why don't we write that down? Now, so let's define that way and that way as our positives. So we're going to have the vertical distance, we don't know. It's going to be minus something. The initial component of the vertical velocity, we don't know that yet. Yes, we do. Sorry, the vertical component is 5.0 meters per second. We don't know the final velocity. We do know the acceleration, and we do know the flight time. In the horizontal direction, we don't know the range. No. We don't know that. We don't know that. We know that's 0, and we know that's also 1.3 seconds. Okay. Show that the initial speed of the projectile is about 12 meters per second. So we have 5.0 meters there per second there. We have that there. That angle there is 12 degrees. So we've got that's the horizontal component, that's the vertical component. They add up to make that there. So we've got this triangle here, or this triangle here, whichever way you want to think about it. And the length of that is what we're trying to work out, because that's the initial speed of the projectile. So we need some sort of Sokotoa thing. So we've got the opposite and we've got the hypotenuse. So sine of 12 is equal to opposite of 5 divided by the hypotenuse. So the hypotenuse is equal to 5 divided by sine of 12. So 5 divided by sine of 12. Oh, why did I get 12 from? That's completely wrong. My apologies. It's 25. Is 11.83 meters per second. So that's the answer there. I've worked it out to an extra decimal place, so we're good. Okay, calculate the horizontal component of the velocity as a projectile hits the ground. So as it hits the ground is this value here, the horizontal component of the velocity here, but that's the same as the horizontal component of the velocity when it's fired. So it's just this length here. So you can use this Pythagoras, or you can do another one of these. I'm going to do another one of these. This time I want to find that length there, so I need tan. So tan of 25 is equal to the opposite, which is 5.0 divided by the adjacent. So the adjacent is equal to 5 divided by tan of 25. So tan of 25, 5 divided by that gives us 10.72253 meters per second. So that goes there. It's 11 to 2 SF, isn't it? but we'll be using that one there. Now if we want to check that, we square that, add them together, and when we square root it we should get that. So let's just double check that. 5 squared, square root that, and we get 11.83, so that's good. Okay. Calculate the maximum height above the starting point reached by the projectile. Give your answer to an appropriate number of significant figures. So this is a sig fig question here. So to do that, we need to think about what's going to happen at the maximum height. Well, at the maximum height, then the at the maximum height, what is the vertical velocity is going to be 0. So S, U, V, A, T. We've got S is the maximum height that we're trying to calculate. U is 5.0. V is 0. A is minus 9.81. And T we do not know because it's not the full flight time. We're not at the end of the flight. So we can't use 1.3 seconds there. So we need an equation with S, U, V and A in it, but no T. So that's got to be V squared is equal to U squared plus 2AS. So V squared is 0 is equal to 25 plus 2 times by minus 9.81 times by the height, H. So we've got 25. We move all of that over there, so we get H is equal to 25 divided by 2 times by 9.81. So H is equal to 1.274 meters. Let's put an appropriate number of sig figs, which is going to be 2. So look, all that stuff's to 2. So it's going to be 1.3 meters to 2 SF. That's what we're going to answer that. Calculate the total horizontal distance travelled by the projectile from its starting point. Well, we can write in the horizontal component of velocity here now. That was 10.72253. And that's the same. So this is not an acceleration question because it's the horizontal one, no acceleration horizontally, which means that we just can simply use that distance is equal to velocity times by time. So that's 10.72253 times by 1.3. So 10.72253 times by 1.3 is equal to 13.939 meters, 14 meters to SF. Okay. Right, last question now. Magnitude of the, so what's this, sorry. Mark with an A on the flight path of figure 1, that's here, the position where the speed of the projectile is greatest. Well, the horizontal speed is going to be the same everywhere. So the speed will be greatest when the magnitude of the vertical velocity is biggest. It's going to be down here, isn't it? Let's just double check that. Yeah, because this is lower down than this, so it's guaranteed. So by the time it gets to here, the vertical velocity here will be the same as the vertical velocity going up there in magnitude. So that'll be 5 meters per second. So it's only going to get faster as it falls. So it's going to be down there. So it's going to be that point there. Mark B on the flight path where the speed of the projectile is least. That's when the vertical component is 0. So that's at the very, 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 very top. So that's there. Cut. And the final part, the projectile reaches its maximum height at time th and finishes its flight at time tf. Draw on figure to a graph to show how the magnitude of the vertical component of the velocity of the projectile varies with time. So we're just talking about the vertical component. So it starts off with a value of 5, not that we need to put the numbers in. But in the vertical direction, we have constant acceleration. This is a velocity time graph. The gradient of this graph is the acceleration. So it's got to be constant. So the gradient has to be constant. And at the top here, the vertical component of the velocity will be 0. So it's got to go to that point there. So we're going to have a nice straight line going there. Then what does it do? Well, if this were not magnitude, just consider for a moment that it was just the vertical velocity, then the acceleration is exactly the same. So that's the acceleration, except it hits the floor here, so it's going to stop. So it's going to suddenly go bang like that as it hits the ground. But that's not the question. It's not asking what the vertical velocity is. The vertical velocity would be this, because it starts off positive, goes up to 0, then goes more and more and more negative. But the acceleration is uniform all the way, so it's a straight line. It's not asking for that though. It's asking for the magnitude of that. And the magnitude of any graph is just the reflection in this axis here of any negative bits. So it's just going to have the exact same gradient going up this time. So it's going to look like that. And then it's going to crash, bang, like so. So let me get rid of the negativity bits. It's not the correct answer. There. So it looks like that. The gradient of that needs to match the gradient of that by I. Okay. And that's it. So with stoppages that took me 40 minutes and explanations, was it hard? Yes, probably, but physics is hard, so you just got to deal with that. Right, done.